There are a variety of spectral decomposition methods. The wavelet transform approach does not require specifying an analysis window length. It gathers and utilizes the required temporal support on a frequency by frequency basis. The Fourier approach utilizes a user-defined fixed window length for all frequency components. Targeting thin beds does not equate to using extremely short windows. The length should be long enough to capture the local tuning characteristics of interest, but not so long that it captures too much geologic content. An overly long window will lead to a geological image that is overly confused and difficult to unravel. The example we see here shows a DFT tuning cube computed from a real dataset. The vertical axis spans 0 to 150 Hz. White is high amplitude, black is low amplitude. If we shorten the analysis window from the 80 milliseconds shown here, we progressively lose the ability to reveal interference details. When we reach the extreme limit of a 2 millisecond window size, which is equivalent to the sample rate of the input data, there is no tuning information left. Each tuning cube trace now exhibits an amplitude value that remains constant as a function of frequency. The window length is so short that we are literally seeing the transform of a spike, which becomes a flat line level in the frequency domain. There is absolutely no value in such a spectral decomposition. It does not capture or reveal any interference. It becomes the equivalent of extracting a conventional full bandwidth amplitude at the one sample and repeating that same amplitude map at all frequencies. If you were to animate through the resulting tuning cube, you would see the same map repeated at all frequencies. If we now slowly increase the analysis window size to 4 milliseconds, to 10, to 20, 40, 60, and back to the 80 milliseconds we started with, we progressively see more and more amplitude character, or interference if you like, along the frequency axis. You are now picking up the type of interference information that becomes useful for thin bed characterization. Let's now look at what happens if you make the analysis window even longer. Going to ever larger windows, say 100 milliseconds, 200, or 400, allows in more and more geologic content, which in turn leads to overly complicated and confusing interference patterns. Broader bandwidths allow you to shorten the analysis window and still reveal the inherent thin bed interference. Narrower bandwidths necessitate longer analysis windows. For typical signal bandwidth limits that extend, say, out to 30 to 60 Hz, it is common to use window lengths on the order of 80 to 150 milliseconds. If you are interested in thicker layer interference rather than thin bed resolution, you need to ensure that the analysis window is broad enough to encompass the thicker reflection package of interest.